Morning to everyone of this webinar. Myself, Rangasamy from Department of Chemistry, Guru Nanak College, host of this webinar. And we, the faculty member of the Department of Chemistry, in association with the IQAC of Guru Nanak College, is organizing this webinar as part of the Chemistry Association activity in the name of Elements 2021. And we have assembled through online to listen the lecture on the role of biopolymers for advanced engineering applications. And the resource person, Dr. Ananda Kumar, Associate Professor, Department of Chemistry, Anna University, is with us. The webinar topic is quite interesting and having more attention in the recent technological era. I hope the lecture will be more useful to understand the utility of biopolymers in the technological application. With this, now I request our beloved Principal Dr. M.J. Raghunathan to deliver the welcome address. Please, sir.
Good morning, all of you. Esteemed resource person of the day, Dr. Ananda Kumar, Associate Professor, Department of Chemistry, College of Engineering, Hindi, Anna University. My dear colleague and beloved Department of PG and Research Department of Chemistry, Dr. Velachery, Organizing Secretaries, hosts of the program, Dr. Rangasamy, my colleagues, Dr. Saroja, Dr. Chitra, Dr. Sridhar, all my colleagues, the Google link, and the people who are in the YouTube also, and my dear colleagues, students, and friends. Today, again, this is a wonderful day. The Department of Chemistry is doing wonderful research in terms of research. Aim and in Sciences Department, Chemistry Department is one of the biggest departments among sciences. Wonderful faculty members. The topic is very interesting. As the role of biopolymers studied by applied chemistry. I know polymer now. Days are changing. Biopolymers, wonderful topic. Definitely, students should take up these topics and do more research on that. Advanced engineering applications. Let me see that how the resource person takes the subject in what way. I am also eagerly waiting. Sir, on behalf of Guru Nanak College, I extend a wholehearted welcome to you, sir. Hearty welcome to you, sir.
Thank you so much, sir. Thank you so much.
I extend a hearty welcome to all my colleagues who are all in the online webinar. Especially, I congratulate Dr. Velachery for arranging a wonderful program and all their colleagues for their support extended to Dr. Velachery and to Guru Nanak also. Madam, do well. Chemistry department is doing wonderful research. If you go on
Thank you.
Website also, the citation of chemistry department is wonderful.
Thank you, sir.
And team, other Dr. Nurjahan team are doing. You can see that citation. Earlier I was thinking that I am this, that. But now, my dear friend Dr. Rangasamy is doing wonderful. I am seeing websites. Chemistry department has got a lot of way to go. Wonderful research is going on, as well as the academics like UG and PG also. My best wishes to the Department of Chemistry for doing wonderful work in terms of academics. And very few words. Thank you, sir. Thanks for the opportunity and thanks for accepting our invitation.
So it's nice to hear such wonderful words from the principal of the college, appreciating the staff members wholeheartedly. It was really inspiring, sir. Thank you so much.
Thank you, sir. Thank you so much.
Now I request Dr. R.M. Velachery, Head Department of Chemistry, to say a few words. Madam, please.
Okay, thank you, Dr. Rangasamy. As our Vice President of the Chemistry Associate, Dr. Rangasamy, and our Principal Sir, today is a great day for us. We have an eminent personality amongst us, and students, we all know about the happenings in the world, and one important topic is biopolymers. We need to know about it. We have a wonderful resource person, Dr. Ananda Kumar. I thank Dr. Jayanti for having initiated this program, and I'm sure we all will be benefited from that. And I also, on behalf of the department, I welcome Dr. Ananda Kumar. Now over to Dr. Rangasamy.
Thank you, madam. Now, Dr. Jayanti will introduce our resource person of this. Jayanti, madam, please.
Yes. Good morning to one and all present here. It's my great privilege to introduce such an eminent person, Dr. Ananta Kumar, Associate Professor, Department of Chemistry, College of Engineering, Gindi Anna University. Sir completed his UG in Urus College. Sir, I wish to mention one more thing. Our principal is also alumnus of your college, I guess. And
Thank you.
MSc,
Very nice to see that.
MSc in Abdul Hakim College, Male Vishara. He completed his PhD in AC Tech, Anna University. Sir did various postdoctoral programs in 3 places, I guess. One is in UK, other one is in Portugal. Sir worked as a consultant for Aishwarya Organics Private Limited. Now he is working as a consultant for that company and as a consultant for Wanson Intermediates and also as a consultant for a nanotech company at Ambattur. Sir has published a lot of papers and his area of specialization are nanohybrid coatings and composites, post epoxy hybrids, and anti-fouling coating. Sir has completed PhD for 4 students and guiding nearly 5 students. He guided nearly 50 MTech projects. Sir, to his credit, he nearly published 62 international papers in international journals and published 8 books. He also presented papers in various conferences and is member of various associations. Sir, if I go through all your profile, I don't want to take your time. With a small introduction, I invite Dr. Anantakumar sir to deliver his lecture. Thank you.
Thank you. Thank you so much, ma'am, for your elaborate introduction. And may I request all the participants to mute your mic so that you know.
Sure, 1 minute, Dr. Anandakumar, one small request. I think you are presenting your whole screen completely, sir. YouTube live video, it is not coming out properly. I request you to give only the PowerPoint presentation, sir.
Okay, and I have only PPT.
No, because if you look into the screen,
Okay.
only PowerPoint is not coming. The whole your now it is all right.
Now it's
Now
okay.
it's all right. Right.
Yes,
Thank you.
yes, Tayo.
Thank you so much.
I request all of them, please mute your mic so that you know we can all listen to this wonderful area of research. So first of all, I would like to congratulate Guru Nanak College for taking this initiative. It's a wonderful initiative. In fact, I always wanted to meet students. So that's the reason why when ma'am called, immediately I accepted the invitation. So the topic is very fascinating, bio-based polymers and the blends for advanced engineering application. Okay, so the agenda of my talk would be background of this investigation. So why we started working on biopolymers and what are the objectives and justification for the need for this biopolymers, an introduction to biopolymers and its application. Besides that, I would also like to give an overview of the work that we carried out in biopolymers. So that is also included in the presentation and followed by results and discussion and conclusion. So what is the need for this talk? You know pretty well that every day there is a pollution and pollution is increasing day by day, which causes various problems and it affects the sustainability of living as well. So the background of this investigation is the world now needs to go green. So that is one of the main reasons why we started working in this area. So with this biopolymers, the sustainability can be realized. You know what is sustainability? Meeting the
Anandakumar, sorry to interrupt.
Yes, madam.
Sir, could you please switch on your video also, sir?
Okay, sure, I'll do that.
Thank you so much.
1 second. I thought it may be a disturbance to the audience, so I thought, no, that's the reason why I switched off. Anyway, I think I'm now visible. Okay. So the world needs to go green with sustainable natural polymers. You know what is sustainability? Meeting the needs of the present generation without spoiling the future generation resource. So that is possible only with the biopolymers. So these are all the reasons why we need to refuse a single-use plastic. So one is the plastic, synthetic plastic is made from fossil fuels, which will last for only 30 years. And a huge carbon footprint. So in my subsequent slides, I'm going to talk about the significance of this carbon footprint. And that is also another reason why we started working in this area. And you can see they are not degradable. They are going to, once you start using the synthetic polymers, their existence is going to be for 100 years or more, which is again a very big issue. It becomes an environmental threat as well. And only tiny percentage is recycled. So though they say recycle is possible, but the recycle amount of the plastic which is being recycled is very minimal. And it leaches into toxic chemicals to food and drink. And thereby, it spoils or it interrupts the food chain. And as a result, again, there is a severe environmental problem, which is because of this synthetic plastic. And it causes hormone disruption and cancers that you know pretty well. And it pollutes our oceans as well, the synthetic polymers. And kills marine animals and birds. And as I told you before, it enters a food chain and becomes a serious issue. So these are all the 9 reasons why we need to switch over to a biopolymers. So the driving forces, as you can see, the growing environmental awareness and stringent e-oil. E-oil means end of life for vehicles. So as far as this e-oil regulations, which was proposed in the year 2005 in the European Union, and they said 40%, almost 85% of the automobile or whatever products they make, they should be completely recycled. 85% of the products should be recyclable. And limitations of landfill, because landfills they account for 40% of plastic waste. So we don't have land to accommodate such a plastic waste material. So that is also another reason. And as per the e-oil regulation, only 5% should be given for your plastic waste dumping. And it is endangering of wildlife as well. So, and besides that, most plastics are not biodegradable. So that is a very important point to be noted. And as I said before, that was in the year 2003, the end of life vehicle by 2015, they proposed that 85% of all new vehicles should be reusable and recyclable weight. So the weight reduction is one of the prime factors they are looking at it. So lightweight with very high strength is what is the portfolio they are looking at it. So when you reduce the weight, obviously you'll be able to reduce the carbon footprint as well. So 10% for energy recovery. So these are all the regulations, these are all the rules they have given us to follow meticulously. So 10% for energy recovery, 5% for landfill. Therefore, the researchers, they have focused attention on natural polymers and the reinforced composites as well. So when you look at this carbon emission is one of the major problems that we are encountering in the recent past, and even still it is prevailing. As you can see, from 1960 to 2000, there is a phenomenal increase in the carbon depletion to the atmosphere. So this graph, which gives an idea about the amount of carbon dioxide that is being depleted to the atmosphere, you can see there is a steep increase. And there is a warning trend is also given by the statistician. And they also believe there is a cooling trend, but as of now, the cooling trend, I don't witness any cooling trend. You can see the glaciers are melting, and there is a sudden fluctuation in the temperature. In fact, a couple of days, around 6 o'clock, you can see there is a heat wave coming in Chennai. So that could be the reason, there is a change in the weather pattern as well. This is mainly due to the carbon dioxide emission. So where you're adding a lot of pressures to the planet, you can see the population growth, again from 1750 to 2000, you can see there is a steep increase in the population, which is to be controlled. That is why I think from Maharashtra, now people, they go for only two children. That is one reason, because it is, again, we don't have land, we don't have resource, we don't have energy to supply this to this material. And similarly, water usage, you can see from 1900 to 2000, you see there is a logarithmic scale increase of water usage. So that is again another problem. Then concentration of CO2, which I already mentioned, you can see there is again a steep increase in the concentration of CO2 depletion to the atmosphere. And number of cars that is being used from 1925 to 2000. So this 1925, that is where the industrial revolution started taking place. There are two different events we should be looking at it. So one is the industrial revolution, the other one is 1935. That is where the Meghalaya came to India. He started, collapsing our entire education system. So this is where things were started taking place in a rapid fashion. And similarly, when you look at the fertilizer consumption, this is the case. So huge amount of fertilizers consumption is also happening between 1925 to 2000. And because of which, as we need a lot of space, loss of rainforests, and then paper consumption, then fisheries fully exploited. So we are adding a lot of pressures to the earth, which again should have an eye. And in order to understand the need for bioplastics for the present scenario, I think I would like you to draw your attention as far as the different planets are concerned. So when you look at the Mercury, the planet which is very close to Sun, you can see the temperature is going up to 465 degrees centigrade, and it can also drop to temperature of minus 184 degrees centigrade. Therefore, Mercury temperature, the planet has no atmosphere and it spins relatively slowly compared to some of the other planets. And when you look at the Venus, the second closest planet to Sun, the highest average temperatures of any planet in our solar system, and it regularly reaches temperature of 460 degrees centigrade. And it has got a lot of greenhouse gases, therefore living is not possible as far as Venus is concerned. So when you look at Earth, that is the third planet from the Sun, and so forth, the only planet known capable of supporting life. So this is what is very much important. You should understand this is the Earth which makes our life sustainable, which is the only planet which is capable of supporting our life. So the average temperature on the Earth is 7.2 degrees centigrade, but it can also vary at other extremes as well. So when you look at the maximum temperature, it was recorded on Earth 70.7 degrees centigrade in Iran. So can you believe this? And the low temperature was minus 89.2 degrees centigrade in Antarctica. So the temperature fluctuation, again, it is related to the pressure that we are adding to the planet Earth. And Mars, so many exploration is going on Mars, which is cold because it does not have an atmosphere to retain heat, and it is relatively far from the Sun. So because Mars has an eccentric orbit around the Sun, it gets much closer at some times than others. So its temperature obviously varies as much as 30 degrees during summer in the northern and southern hemispheres. So the minimum temperature of Mars is approximately minus 140 degrees centigrade, and the highest is 20 degrees centigrade. So again, there's no possibility that we can live on Mars. So owing to the other above reasons, one has to understand the importance of our Mother Earth, and we have to always keep the Mother Earth at in a conducive atmosphere. So for which we have to do certain operations so that we can realize the sustainable living as well as without polluting the environment. So that is also another important reason for our research work towards the bioplastic. So when you look at this global warming climate change, you can see half of the solar energy is absorbed at the surface. So what happens when too much of CO2 is depleted to the atmosphere? It forms an insulating layer over the Earth's surface. As a result, most of the heat radiation that comes into the Earth's surface, it is not reflected back. So our prime objective is to reduce this layer, so many ways as possible. So one of the possible ways by which the layers can be reduced by switching over to your biopolymers. You can see when it absorbs a lot of energy, what happens? It evaporates water and adding most important greenhouse gases to the atmosphere over the Earth's surface. And when water condenses, it releases energy which adds too much heat energy to our Earth's surface. So about 30% of incoming solar energy is reflected by the surface and the atmosphere, but that is getting affected by our man-made operations. So only a small amount of heat energy emitted from the surface passes through the atmosphere. Therefore, this is mainly because of the carbon dioxide insulating layer that is responsible for not letting too much of energy that is being reflected back to beyond Earth's surface. So this has to be taken care. And you need to frame the question. Therefore, keeping all the above things into consideration. So one has to have an idea about the questions, the following questions you must have when you are working on any area of research, which could be a polymer or metal or whatever it is. So these are all the questions that one should have in your mind. So what is the carbon footprint or profile of your product? So have you ever thought of this? This carbon footprint concept is catching up like anything. So what is the amount of carbon dioxide that is left to the atmosphere for any materials that you produce? So what is the carbon footprint or profile? Or are you developing your own carbon footprint? Supposing if I use biomaterial, so what happens? It's carbon footprint. So you have to compare the carbon footprint of your synthetic polymer as well as your biopolymer, and then try to have an understanding between them. Then for which you have to understand the life cycle assessment, which is to be done for all products, whatever products that you develop, which whether it is for synthetic purpose or academic purpose or industrial purpose. So this life cycle assessment is mandatory nowadays. So what it says, you have to take the cradle to factory grade. That is where you are getting the raw material. From the raw material goes to factory. From the factory, it is converted into product. From the product after usage, it is again left to the atmosphere. So for each process, you'll have to calculate the carbon depletion for unit operation of each processes. So what are you doing to reduce products' carbon footprint? So what is your contribution for this? How to reduce this carbon footprint? And are you moving towards a zero neutral carbon footprint? And in order to have an idea, you must also take into account the environmental footprint as well, which includes esterification, acidification as well. So when you are calculating the carbon footprint, besides carbon footprint, the environmental footprint is also to be summed up, so that the total carbon footprint is to be calculated for any product or process. Any process you are doing, you have to calculate the carbon footprint. From the process, you get a product. So what the product also, when it is being used, what is the amount of carbon dioxide or carbon footprint which is coming up from this product is to be noted down properly. And sustainability. So when you talk about sustainability, only when you do this all these things, the sustainability becomes possible. That is, which includes social impact and macroeconomics, and not just environmental as well. So carbon footprint contributions, they are divided into material carbon footprint and process carbon footprint. So these are the two things that one has to understand. So what happens when you are replacing the fossil carbon with the biocarbon? So that is what my topic is, talk is about today. See the importance of this biopolymers, that becomes very important because when you say the carbon footprint is substantially reduced, obviously the polymer which is going to release very less amount of carbon dioxide is my choice. So when you look at the process carbon footprint, so impact of converting feedstock to product, as I told you, you have a raw material. The raw material goes to factory wherein it is converted into a product. So during one, what is the carbon footprint which is eliminated? So carbon emission from all stages of unit operation to convert the selected carbon feedstock to product is to be calculated. Similarly, when you are getting the product from this source material, so what is the carbon footprint? Similarly, when the product is being used, what is the carbon footprint that is coming out? So these are all the things that one should have in their mind. Similarly, as I told you, besides carbon footprint, you must have an idea about the environmental footprint, which is about your human health, ozone depletion, eutrophication, acidification, and photochemical smog. So these are the two things that are very much important whenever you are making any product for any particular application, which includes material carbon footprint and product process carbon footprint as well. Okay, so when you look at the material carbon footprint, so what is the impact of the material or product's carbon footprint on the environment? Say, for example, I'm using 100 kgs of polyethylene. At the same time, I'm also using 100 kgs of biopolyethylene. So 100 kgs of synthetic polyethylene will result in net how many kgs of CO2 released in the atmosphere to be calculated. In comparison, you should also calculate what is the net kgs of CO2 released to the atmosphere when you are replacing your fossil carbon with the biocarbon. So 100 kg of polyethylene terephthalate, PET is a commodity plastic which can be seen at a household. So PET, you have carbon 2 glycol and carbon 8 terephthalic acid. So it is an ester. So alcohol plus carboxylic acid will normally result in ester. Will result in net how many kgs of CO2 to the atmosphere. So that should be calculated. So material carbon footprint and carbon process carbon footprint. So what is the material I have? I have the raw material, oil, coal, natural gas, from which the plastics are derived. Pretty well plastics are the byproducts of crude oil. So oil and coal, natural gas, they are converted into naphtha. Naphtha, which is further converted into ethylene or propylene, which are all the monomers. When they are subjected to polymerization, you get the corresponding polymers, polyethylene or polypropylene. So this is one of the process by which you get the polymers. Whereas the same polymer, ethylene propylene, can be obtained from biomonomers as well, for which the sources is crops or residues, which includes corn, soybean, or sugarcane. So instead of getting your ethylene from natural oil, natural gas, or coal or crude oil, I can also get the same ethylene from the agricultural feedstock like corn, soybean, and sugarcane. So what happens? When these crops or residues, they are converted into biomonomers or sugars. So as you can see, you can get polylactic acid and polyhydroxy alkalates. That is also a bio-based polymer. Then this biomonomers can be converted into ethanol. Then ethanol can be converted into ethylene or propylene. From ethylene and propylene, you can get the corresponding polymers, polyethylene or polypropylene. So what I'm doing here is I'm just simply replacing the fossil carbon with the biocarbon. And I'm also calculating the amount of carbon dioxide that is left to the atmosphere. So this is the graph which is very interesting to all of you. As you can see, 100 kgs of polyethylene, which is a synthetic polyethylene, which releases 314 kgs of CO2 emission. You see there is a lot of CO2 being emitted when you are using a synthetic polymer which is obtained from crude oil. And similarly, you can also calculate the amount of CO2 that is left into the atmosphere for 100 kg of polyethylene terephthalate, PET. So you can see it is almost somewhere between 225 to 230 kgs of CO2. So in both cases, the synthetic polymers, they emit too much of CO2 to the atmosphere. You know what are the consequences of CO2? CO2, it forms an insulating layer. As a result, too much of heat is coming to your atmosphere. Our Earth planet, you are adding too much pressure, and you are giving trouble to yourself as well. So what happens when you are switching over to biocarbon? So when I am switching over to biocarbon, you can see there is no carbon footprint at all. Zero carbon footprint is witnessed in the case of biocarbon. Therefore, your strategy could be, instead of getting a polyethylene or polypropylene from crude oil, you can always switch over to agricultural feedstock from which the polyethylene or polypropylene or even other polymers can be obtained. So that could be a strategy that you should be looking at in the future. So material carbon footprint, so many kgs of CO2, as you can see, the biopolyethylene or biopet will not leave any CO2 to the atmosphere. So that is what I would like to follow. So this is a very good strategy, because you get the polyethylene that you wanted, and besides that, it is not polluting the environment. So that is something very interesting to the researchers. That's why most of the researchers nowadays, they are focusing the research towards these biopolymers. So when you look at the global carbon management, it takes its nature's way. As I told you, when you look at it, you have carbon dioxide, and then carbon dioxide is converted into biomass. This biomass that takes 10⁶ years to get converted into fossil resources, and this fossil resources through chemical industries, you are getting the corresponding polymers, chemicals, and fuels. As you can look at the right hand side, it takes time-consuming process, and the process takes a lot of time, and also the product which leaves a lot of CO2 to the atmosphere. So my new strategy will be, once you get the new carbon biomass and agricultural crops, instead of following the right hand side operation, I would like to prefer the diagonal operation, wherein the new carbon or biomass agricultural crops can be converted into your polymers are chemicals through biochemical industry. So that is a new pathway many people are now looking at it. And the major advantage is the time. There is a lot of reduction in time. So you get your product very quickly, unlike the product which is obtained over a period of years. 10 power 6 years is very much, it's too much. So that is not conducive. And at the same time, when you switch over to this particular pathway, you are also avoiding the carbon dioxide emission to the atmosphere. So this is the preferred strategy for many researchers nowadays. So you can get your new polymeric material, that is your polyethylene or polypropylene, can be obtained from this way. And the new renewable carbon footstock is what I'll be interested in, because it leaves a zero carbon footprint to the atmosphere. And as a result, you can see this is what I told you. So naphtha oil is converted into naphtha, ethylene oxide. So you get ethylene glycol. So that is one way of doing it. Instead of that, I can use this crops as a raw material. I can get biomonomers, ethanol, then ethylene. Then you can get ethylene glycol as well. Similarly, you can also get the acid from the same strategy. So you try to get the corresponding polyethylene terephthalate. So you'll get biopet. So in fact, many companies have now started using these products. So Walmart is one of the companies which is very much interested in the conversion of PET containers to PLA. So what the Walmart has done, they have replaced all PET containers to polylactic acid in grocery retail, and they found there is a phenomenal reduction in the carbon dioxide. So they estimated the energy savings almost equal to 800,000 gallons of gasoline in a year. So Walmart has cited reduced fossil fuel usage, and they are switching over to biocarbon instead of the petroleum carbon. So they have lots of products, as you can see, plenty of products are available from the Walmart. And similarly, you can see, the CNG savings are it is 11 lakhs 957,000 pounds of CNG can be saved, is equal to eliminating the CO2 emission from driving a car 23 million kilometers in a year. So greenhouse gas reduction is the second part of the messaging, despite lower US consumer awareness. But US, still people are reluctant to use this. But besides their reluctancy, still, there is always this greenhouse gas reduction is the second part of the messaging. So I think in India, we'll also witness the same situation maybe in future. So the green future, when you look at it, the strong need for new and reliable materials, and for which the prerequisite for this new future should be recyclable. The materials that you are developing should be recyclable, should be reusable and biodegradable, and they should be obtained from sustainable resources, because I've indicated the path by which you can get the biopolymers from agricultural crops, which are going to leave no CO2 to the atmosphere, and yield properties comparable to common plastics. So make sure that the biopolymers obtained from agricultural feedstock should have similar properties that of your synthetic polymers, and they can be produced at an affordable cost and be resistant to weathering. So all these things can be possible by the use of natural polymer-based materials and their blends. Okay, so justification for my talk would be both sustainable development and green economy require brand new materials. Natural polymers, biopolymers, and synthetic polymers based on annually renewable resources are the basis of the present century portfolio. And both the bio-sourced materials gradually will replace the currently existing family of oil polymers, and they become cost and performance-wise competitive. So that is the justification of our work. So with that, I have given the background of the investigations. So if you have any questions in between, you can ask me. So that is the reason why we are now switching over to bioplastics. What are the reasons, or what is the pressure that you are adding to Earth? And the only sustainable planet is Mother Earth. So you will have to keep the Mother Earth at a conducive atmosphere, which is possible only by means of using the sustainable materials. And I've also indicated the prerequisites for the new green economy materials. So if you have any questions, you can ask me. Otherwise, I can just continue the introduction. So if no further question, let me move on to this natural polymer. So I'm going to give an introduction about natural polymers. So natural polymeric materials have been used throughout the history. In fact, it is prevalent from our ancestral period as well. From the Neanderthal period itself, the natural polymers were used. So you can see our ancestors have been using this natural polymer for clothing, decoration, shelter, tools, weapons, and writing materials as well. So some of the polymers that I've indicated fall into the category of natural polymers: starch, cellulose, protein, air, silk, DNA, and RNA, which you are very familiar with. And this is the chronological development as far as natural polymers is concerned. As I told you, the natural resins, they are prevalent from early history, that is from Neanderthal period. So actually we are all Homo sapiens. Neanderthals are our previous ancestors. Okay, so Neanderthal period itself, the natural resins like shellac, rosins were available. Then in 1910 you have modified phenolic, 1920 nitrocellulose, then air drying oil modified polyester in 1927, urea formulated polymers 1929, chlorinated rubber 1930. So the list goes on till polyethylene you have 1948, 46. So biopolymers are obtained via polymerization of bio-based raw materials through engineered industrial process. So when I say engineering, please don't get confused, because engineering is nothing but the advancement of science. So advancement of science is engineering, and advancement of engineering is technology. Therefore, when you want to realize engineering and technology, science is very important. So all students who have opted for this science courses should be really proud of, because without science there is no engineering, there is no technology. So the biopolymers, they are obtained by the polymerization of bio-based raw materials through engineered industrial process. So the raw materials of biopolymers can be from plants or from animals, or they can also be synthesized from biomass using enzymes. In fact, one of my PhD students was synthesized a polymer from the soil using microorganisms. So that is also possible. So it is not that you can use the biological feedstock, that is corn, agriculture feedstock, as a raw material for production of polymers. You can also use soil as a source for the production of your polymer. That is also another fascinating strategy. So you have to understand, before that you must understand the difference between the bio-based polymers and biodegradable polymers. So what is meant by bio-based polymers? So when I say bio-based polymers, the plastic products which are made by transforming bio-based materials either exclusively or in combination with the non-bio-based material. That is, supposing if I have a polyethylene, so I have 90% polyethylene obtained from your agricultural feedstock, 10% obtained from your petrochemical feedstock. So even that combination, you can call it as a bio-based polymer. So it could be a combination of exclusively, that is 100% natural material, or 90%, 90-10 combination as well. Both of them can be called as bio-based polymers. So a bio-based material is one in which the significant portion of the carbon is derived from the renewable resources. So you have to get the carbon from the renewable resources like corn, soybean, grasses, or other plants. As I told you, this, instead of using the petrochemical feedstock from crude oil, you can use these renewable resources for the production of this carbon. So that is called bio-based polymers. Then comes the biodegradable polymers, the plastics, either bio-based or petrochemical based. It could be a bio-based material or petrochemical based material. They are designed to break down for complete assimilation by microorganisms. That is, a plastic product is able to undergo degradation by the action of heat, microorganisms, or moisture. Then you can call it as a biodegradable polymer. So bio-based polymers can be biodegradable. So please understand the difference between the bio-based polymers and biodegradable polymers. And examples of your biopolymers, you can say there are plenty of functional groups are there. You can say polyesters belong to this category, polylactic acid. Though it is called as a polylactic acid, it's a misnomer. So it's a lactide only, it is polylactide. Similarly, polyhydroxy alkanates, which is also an ester. Then polyphenols, you have lignin, tannin, and humic acid. Then proteins, you have silk, soy protein, and corn protein. And lipids, you have waxes, surfactants. And polysaccharides, you have xanthan to starch. And you have specialty polymers, as I told you, shellac, natural rubber. Even nylon can be obtained from the natural ore. Instead of using your terephthalic acid, or adipic acid. You can use castor oil because the oils are fatty acids of unsaturated and saturated fatty acid combination is your castor oil. So why biopolymers? As I told you, enough I have indicated the reason why we are switching over to biopolymers, because of all the fossil fuels will last for only certain years, and not only that, they pollute the environment. And for each stage of unit operation, when you calculate the carbon dioxide emission, which will be more in the case of fossil fuel. Therefore, obviously, we have to switch over to the biopolymers. So USDA's byproduct chemistry engineering research, they focus on creating new polymer technologies. So this technology is already realized by US companies. As I told you, one of the companies, Walmart, they've started developing a lot of products. In fact, European Union also, they've started plenty of bio-based products for your consumer application, engineering application, and specialty application as well. And the reason is, the most synthetic polymers are not biodegradable. So that is the reason why these biopolymers becomes inevitable. And apart from that, when you look at the advantages of biopolymers, they are lightweight material, they are corrosion resistant, they are abundantly available, they are eco-friendly, and they are compostable and biodegradable, and they have thermoacoustic insulation properties, and most of all, it is less expensive. So that is very attractive. So when you look at the bio-based polymer market, from 2011 to 2020, you can see the total production of bio-based polymers 265 million tons. That is total production of polymers. So among them, the bio-based polymers will contribute 3.5 million tons, and their market share is about 1.5%. That is in the year 2011. But it is almost get double in the year 2020. You can see the production is overall production of polymers 400 million tons. And bio-based polymers is 12 million tons, and bio-based polymers market share is 3%. So there is a significant improvement in terms of production as well as its market share, which can be witnessed from the graph. You can see plenty of biopolymers like PLA, starch blends, polyhydroxy alkanates, then PBAT, PBS, polyolefin. You can see the usage is getting increased day by day, which shows that people are now really interested to use this material instead of synthetic polymers. Similarly, you can also have the statistics as far as the biodegradable polymers. In this case also, there is a phenomenal increase in the use of biodegradable polymers. From 2014 to 2020, you can see it is there is a phenomenal increase in the use of biopolymers. The global biodegradable polymer market should reach 5.6 million pounds, billion pounds by 2021. So it is almost getting double from 2.4 billion to 5.6 billion. You can see there is a significant growth, compound annual growth rate, CGAR. It is 18% from 2016 to 2021. So compound annual rate, the rate is one, which is really it is going up in the case of your biodegradable polymers. And moreover, the biopolymers, they act as a link between modern and traditional industries. In fact, many automobile cars which you witness during these days, like Audi, Volkswagen, Benz, and Daimler Chrysler, and even Hummer, the car, they make use of this biopolymer. So it is a link between the modern and traditional industry, and it is used for size reduction and even for performance improvement as well. So that is the reason why people have now started using the bio-based or biodegradable polymers for the production of various automobile components. So, and you should understand that it is not confined only with the automobile industry. So that is what students should understand. Since I'm emphasizing on automobile products, that does not mean that this polymers can find application only in automobile industry. So you can try to explore the use of this material for various industries. So it is capable. Okay. And the motivation for biocomposite research, you can see plenty of people are involved. Farmers are involved in the biopolymer research. Processors are involved. Then plastic composite manufacturers are involved. Then commodity groups are involved. And apart from that, university people and the industry researchers are also involved. So it is a collaborative initiative. So biocomposite material will emerge as an important Indian material as the technology evolves through strong collaboration by several phases of the entire production. So bio-based polymer production routes, you can produce bio-based polymers for various production routes. So one is polymers directly extracted or removed from biomass. Biomass could be a source. You can extract polymer from the biomass. That is one of the ways by which you can synthesize the bio-based polymers. The polymers which are obtained from these routes are polysaccharides, which are starch and cellulose. You can also get proteins, casein. Casein actually it's a milk protein. In fact, one interesting information I'd like to share with you. Casein was the wood adhesive before the discovery of your phenol formaldehyde. In fact, phenol formaldehyde was discovered during 1930 to 1931, I guess. So before that, casein was one of the excellent wood adhesive. It's a milk protein actually. Casein is a milk protein which was used as a wood adhesive. And similarly, you can also get bio-based polymers by classical chemical synthesis using renewable monomers. That is polylactate, the biopolyester formed by the polymerization of monomers. So instead of using biomass as a source, you can have the monomer, which is then polymerized to get the corresponding polymer. That is the second route of production. The third route of production, polymers obtained with the help of microorganisms. As I told you, microorganisms are capable of producing polymers. So the microorganisms include bacteria. As I told you, one of my research scholars was able to use the gram-negative bacteria which synthesize Cudlin. Cudlin is one of the polymer which is finding plenty of application in biomedical and healthcare. Therefore, she was able to get 18% of polymer production from the soil. In fact, we collected the soil from the Kuam soil, which has a lot of microbes on it. So we started using that, and we have got wonderful and promising results. So the polymers obtained from microorganism route could be polyhydroxyalkanates or bacterially synthesized cellulose. So you can have a comparison, bio-based chemical and the referent petrochemicals. You can have ethyl acetate, it can be bio-based, ethylene can be bio-based, adipic acid, acetic acid, N-butanol, PTT, PHA, PLA, FDCA, and succinic acid. So all these materials can be obtained from this bio-based origins. And biodegradable polymers, you can see the production route. They are obtained from biomass products. They are also obtained from microorganisms. From biotechnology pathway, you have polylactic acid. From oil products, you can have polycaprolactam, polyester-imides, aliphatic copolyester, and aromatic oils. So for oil production, vegetable oils can be used as a source from which you can synthesize this bio-based polymers. So this is about your biodegradable polymers production. And the types of biodegradable polymer, I would like to give an introduction about this biodegradable polymers. You have different types. So photobiodegradable polymer, that is the polymers which can degrade under the influence of light. Then peroxidizable polymers and photolytic polymers and hydrobiodegradable polymers. So these are all the different classification of biodegradable polymers. Okay, so hydrobiodegradable polymers, the polymers which can degrade under the influence of moisture or water. So hydrobiodegradable polymers undergo hydrobiodegradation. Hydrobiodegradation is initiated by hydrolysis. So you know what is hydrolysis? Hydrolysis is nothing but breaking of bonds using water. That is called hydrolysis. So the polymer is capable of undergoing degradation by the action of water. And you also have oxo-biodegradable plastics. So it will degrade in the presence of oxygen, and the process is accelerated by UV and heat. So you also have a oxo-biodegradable polymer which will undergo degradation under the influence of oxygen. And it can be recycled during its useful life with a normal plastic. Therefore, when you ask me which polymer you would prefer, I would always prefer oxo-biodegradable polymers over hydrobiodegradable polymers. So why I choose oxo-degradable polymer? Because usually it is made from a byproduct of oil refining and can be made from recycled plastic. And the main difference is it emits CO2 while degrading and forms biomass. Therefore, it is somewhat the product can be, it is non-toxic because the CO2 is converted into biomass, from which again you can try to synthesize the polymer and can be incinerated with a high energy recovery, whereas a little cost is involved in this biodegradable plastic. When you look at the hydrodegradable polymer, it is made from fossil fuel. They cannot be recycled, and it emits CO2 rapidly while degrading. Therefore, when you look at it, a sustained release of CO2 is possible in the case of oxo-degradable polymer, whereas hydrodegradable polymers, this is not the case. And the cost is very expensive as well. Therefore, owing to the reasons, I would prefer to use oxo-biodegradable polymer. So types of biodegradable copolymer. Instead of polymer, you have homopolymer, you have copolymer as a combination of two different monomers. You can get the corresponding copolymer. You have graft copolymers, you have block out copolymers as well. So grafting, you can do it in different ways. Grafting onto method, grafting from method, and grafting through method. So these are all the three different strategies by which the graft copolymers can be obtained. So you have different structural combinations. Like one, you have a regular stereotype, it is called a stereoregular polymer. So you have a same fashion, that is the backbone will have same linking segments. Whereas you have alternate copolymer and then a random copolymer as well. Three different combinations are possible, and three methods synthesis is possible as far as the graft copolymers are concerned. So grafting onto method, it is nothing but coupling reaction between a functional backbone and end groups of the branch. So when you see, this is the backbone. Backbone, as far as our body is concerned, our bone is our backbone. So bone is the one which gives you a shape. Similarly, polymer, this is the backbone. In the backbone, you have the linking segment which is having a function too. So this is a backbone. This is a coupling group which has a function group. Okay. So what happens? The backbone containing function group is capable of reacting with the incoming linking segment, which is also having another function group. Therefore, a coupling reaction between A and B takes place. You get the corresponding grafting onto method polymer. Similarly, grafting from method, the backbone is chemically modified into active surfaces. So instead of having functional groups at the backbone, you can have active sites at the backbone. Okay, so by means of this, the active centers can be used as a site for polymerization. The active sites form branch by copolymerization. That is called grafting from method. And grafting through method, it is also known as a macro monomer method, in which you have a low molecular weight monomer is taken and it is subjected to a polymerization when it is made to interact with a macro monomer. So you have a oligomer and macro monomer in the presence of an initiator, which is a it could be any initiator and catalyst. So when you do this, you can get grafting through method polymers. So biodegradable composite also you can provide. You know what is a composite? Composite is a combination of matrix and a reinforcement. So the matrix could be your bio-based polymer or biodegradable polymer. The reinforcement could be your desire, according to your desire. So the characteristics of biodegradable composites, they are biodegradable, they are renewable and recyclable, and they have lower manufacturing cost. So when you look at the types of biocomposite, you have polylactate natural fiber composite, then polyhydroxyalkanate natural fiber composite, and thermoplastic starch natural fiber composite. So these are all the three different types of biocomposite materials. So advantages when you look at the polylactic acid biocomposites, they are low cost, they are abundantly available, high specific properties, lack of residue upon incineration. So when it is subjected to incineration, it is not going to leave any CO2. This is what we already saw. And the polyhydroxyalkanates, again, renewable resources, increase in tensile strength, so which is used for some mechanical engineering application. Then thermoplastic starch, increase in tensile strength, less humidity absorbance, and lightweight metal. So these are the properties which can be exploited for industrial engineering applications. So when you are looking products for industry, especially the mechanical properties should be very high. So, and the barrier property should be very high. Therefore, you can choose these materials for industrial application as well. So, polyhydroxyalkanates, it's a linear polyester. Polyester, again, it is ester is nothing but alcohol plus carboxylic acid. And it is produced by the bacteria to store carbon and energy. More than 150 different monomers can be combined with this family to give materials with extremely different properties. So, polyhydroxyalkanates is one of the family of your biopolymers. Similarly, thermoplastic starch, it is a starch-based plastic. Formation of it requires disruption of starch granules and the supermolecular structures, dissociation of complexes with the lipid and melting of crystals with the assistance of added water. This is how your thermoplastic starch is produced. And it is suitable for the production of drug capsules by the pharmaceutical sector. So this thermoplastic starch is used as a carrier for drug materials. And starch, you can see 70% of the industrial cornstarch is made into adhesive. So adhesive is another fascinating industry where people should be interested in, because adhesive is a substance, a material which binds two different dissimilar materials together. Supposing if I want to bind a metal with plastic, that can be possible only with the application of adhesive. So adhesive area is again one of the fantastic areas which you can think of. And the natural adhesives, again, they have plenty of applications. So 75% of the industrial cornstarch is made into adhesive for use in the paper industries, because paper, it can be made into cationic, anionic. So for that purpose, they make use of adhesive. Then cornstarch absorbs 1,000 times its weight in moisture, and it is used in diapers. So diaper, pretty well, it is used for infant care. So the diapers, again, this can be made using cornstarch, which is capable of absorbing water 1,000 times. Then starch plastic blends are used in packaging. So besides that, they are also used in the packaging industry. And starch blended or grafted with the biodegradable polymers such as polycaprolactam are available in the form of film. So you can also a combination of starch with natural polymers like polycaprolactam starch blend combination can be used as a film for packaging application. And blends with more than 84% starch are used as foams in polystyrene. So you can also make products like thermocol using this starch material in combination with the other polymers. Then polylactic acid, this is one of the forerunners as far as the industrial applications are concerned. In fact, one of my PhD students, recent past, last week, he defended successfully for his PhD work. So he has carried out entire work on polylactic acid. In fact, we have got a patent from Anna University yesterday only, that was finalized. So we made a wonderful industrial product using polylactic acid, which is used in the form of coated abrasive. So which I'll be talking later. So polylactic acid degrades primarily by hydrolysis and not by microbial attack. Therefore, it is prone to hydrolytic degradation. So it falls under the hydrodegradable polymer, but still it has got some edge properties. As a result, only it is used as a forerunner as far as the industrial polymers are concerned. And when it is buried in soil, it will take 180 days to get degraded. But in our one of my research, we found that when it is put into coconut, what happens? It will undergo degradation within a week's time. So this is what we found in our research. So we kept this polylactic acid film in coconut, open coconut actually. So that undergoes degradation within a week's time. So we can try to expedite the degradation process with various natural process as well. That is possible. And polylactic acid fabrics have a silky feel and good moisture management because it has got a methyl group. That methyl group is responsible for offering hydrophobic behavior. In fact, the contact angle is greater than 80. So this can be used as a hydrophobic material. And that is also another reason why we used the polylactic acid for industrial product. And you can also make copolymers of lactic acid and glycolic acid. That is going to offer you a unique combination of properties, and especially finds application in healthcare, like the orthopedic surgery. And polylactate, some of the products that you can witness from the slide, you have plenty of products. Disposable cups can be made, and casing of a memory stick can be made using polylactic acid. Plastic bottle, food containers, then cutleries and crockeries, a disposable bag as well. This is the use of polylactic acid for various engineering applications. And similarly, they do find application in healthcare. As I told you, they can be made in the form of scaffolds. They are used for drug delivery. They are used for sutures and vascular grafts, skin tissue repair, and medical implants as well. So these are the various applications of polylactic acid. So where are biodegradable polymers needed? As I told you, from the previous slides and all, you have witnessed the applications of various biodegradable and bio-based polymers. They find application in the form of a trash box, a loose film foam, and food containers. In case of consumer goods, they are used as razor handles, toys, In case of medical applications, you can see they are used for drug delivery, sutures, bandages, and orthopedic application, and they do find application in cosmetics and coatings as well. So you can see the application starting from coatings to rubber industries. You have plenty of applications by your bio-based and biodegradable polymers. And when you look at the use of biopolymers, geothermal, geotechnical engineering, you can see the biopolymers, they are used for slope reinforcement, they are used for quick dewatering of blockage, and the waste material can be used as a manure for vegetation improvement, and they are also used as a erosion protection material because they offer some barrier property. When they are mixed with the proper combination of different additives, even the biopolymers can be made as a barrier material, and as a result can be used for erosion protection. Then they are used for earth and adobe construction. Then demixing and ground improvement can be possible. Biopolymer soil mixing in site is also possible. Then site aeration, dust reduction. Since you are using biopolymer, obviously it leaves no CO2. There is a phenomenal reduction in the air pollution as well. And in situ biopolymer culture and supply plan can be realized, and non-cement earth road construction material can be realized from biopolymers. And 3D printing, this is another fascinating area. Students can think about it. The biopolymers can be 3D printed. As of now, the market makes use of polylactic acid, polyamides, polyurethane. These are all some of the biopolymers which can be 3D printed. Actually, the 3D printing is mainly used for producing complex articles. Whenever you have a complex shapes like the scaffolds and all, which can be made by using a conventional molding operation. So the 3D printing is a fascinating technique wherein you try to produce some complex structures for which biopolymers are the source materials. So you can use the following biopolymers. Cellulose can be used, hemicellulose can be used, xanthan, then glucosamine, and xyloglucan. These are the polymers which can be used for the production of various materials. So when you look into the applications of this bio-based polymers in healthcare, you can see they are obtained from wood, bamboo, agricultural product, residual product. From plants and animals you get the biopolymers, and through sequential extraction you get the polymers. You see the cellulose derivatives, they are used as a ink in suspension, hydrogel and filament. And hemicellulose composites, again they are used as a ink form, in solution form, hydrogel form and filament form. So these forms can be used for 3D printing. And solution filament, again you can use a lignin derivative, starch derivative, alginate derivative, chitosan which is obtained from crab shell. Chitosan is obtained from animal shell. You can get chitosan. Chitin is a material. When you do the degradation of chitin, you will get the chitosan. And then you can also use protein derivatives in the form of ink, which can be 3D printed. So the products can find application biomedical, and apparel, interior and architectures, and customized food fabrication as well. So you have various applications for biomedical, apparel and customized food fabrication. And this one, since we are in COVID season, I thought I should provide information about this particular 3D printed adapter, which was made by this company Materialize. So they developed a polymer based 3D printed component which makes breathing easy. So they developed a solution to deliver oxygen and create high positive pressure without the use of ventilator. So you need not have a ventilator using this material, which is made up of plastic. So they have used a plastic resin piece with 3D printers, and they were able to produce this 3D printed polymeric material, which will ease your breathing. So that is one of the main things. So if you could allow me, shall I play a video? This can be interesting. If you want, I can play the video. Do you have time for this?
Yes, sir.
Okay. So this one, this is a very interesting product which they have recent past they have made. Maybe 1 second. Hope it is not boring. I guess if you have any questions, you can ask me in between.
interesting session.
Now, audience, participants can unmute your mic. You can ask your questions.
Let this video get over, Raghusaami. Later on, they can.
Do you hear the voice?
Yes, sir.
Additive manufacturing can provide a fast solution in many cases. We all know that there's a global shortage of ventilators, and many parties are looking at finding a solution for that and using additive manufacturing to upscale production. We have tried to take a different perspective on this. With the shortage of ventilators, physicians are looking for alternative ways of creating positive pressure on the lungs of patients. We have 3D printed a connector that keeps together a non-invasive mask, a filter, and a PEEP valve that can be used to create this positive pressure. This combination of solutions that are standardly available in the hospitals will then be held together by that connector to create a non-invasive PEEP mask or a NIP mask. There's no need to use a ventilator with those.
Question: when we start with the mask, well, I think when the patient is deteriorating in the sense that there is a much more higher need for oxygen at that time, probably it's the good time to switch from a just pure oxygen mask, where you just deliver oxygen, to a mask that is also delivering this positive pressure in the airways, pushing back the fluid in the lung, and then a better uptake of oxygen. So we think if we do that, first of all, it's a safe thing to do, because it's a mask that is a fitting mask and there is no leak. That means there is not so much risk of spreading the virus in the environment. That's the first thing for the caregiver. It's a safe thing to do. And for the patient, of course, it's not so much invasive.
To install it on the patient, you just have to connect it to the oxygen supply. It's a simple system. In a matter of days, we were able to go from ideation to an actual proof of concept that we tested together with the pulmonologists. And a few days later, we were ready for verification testing on healthy humans. To realize this quick turnaround, we really relied on our medtech know-how as a company that's been doing this for years and that has been working together with some of the biggest hospitals and some of the biggest medical device companies.
The 3D NIP connector is available as it stands, and we're fast-tracking it through the regulatory process. We are supporting physicians to set up a clinical trial to find out more about the best indications to use this passive NIP mask on COVID patients and define clinical pathways for hospitals to use. We understand that in the meantime, there will be many hospitals and physicians in dire need of solutions because of the shortage of ventilators. And we're very open to collaborate with those physicians to find solutions to make the connector available to them. We're obviously also very open to collaborate with industrial parties that can help us bring this solution to patients around the world in a faster way.
So that was very fascinating, I guess. So let's go to where I left. Sorry.
Today I'm going to talk about the respiratory evaluation and management of people living with ALS. I have no financial disclosures at
Sorry
this
for
time.
the trouble once again.
The learning objectives
Let me close it.
So we're going to talk about a little bit about some ALS characteristics. We're going to talk about progression in evaluation. We're going to talk about modes of non-invasive ventilation. We're going to talk about some troubleshooting issues with non-invasive ventilation.
I'm not able to do this.
Beyond non-invasive ventilation. So just my one page.
Another window has opened, sir. Conclude it.
Yeah, that's what I'm trying to do it.
There's no ethnic or racial.
So before that,
progressive motor neuron disease has effects on the upper motor neuron, which is spasticity, dysarthria, dysphagia, lower motor neurons, extremity weakness, atrophy, and manipulation. Respiratory failure is the most common cause of morbidity and mortality in people living with
Sorry. So.
No problem, sir.
Sorry. Can you see my slide now?
Yeah.
Yes, sir. Yes.
Okay.
Just
so that
kindly.
was about.
Yeah. Now it's all right.
Okay. So this was the product which is put into use the recent past. So credit goes to the chemists and physicists people. And as you can see, we've got a lot of things to do. So as I told you, being a chemist, you should be really proud of. We are the one who can support those doctors at this situation. In fact, the drugs and all, again, our role is very important. So what are the opportunities? What are the opportunities for biodegradable polymers in terms of vegetable oils? As you can see, it is a combination of saturated and unsaturated fatty acids, which can be modified according to your desire, and you can make plenty of polymers and subsequently into products. So you can see the composition of vegetable oils. You have various oils like oleic acid, linoleic acid, and whose iodine values also, it is very interesting. So according to the iodine value, you can use a corresponding polymer or corresponding fatty acid, and which can be used for various products make. So you can see eleostearic acid, palmitic acid is present in our coconut oil, which is in fact good for your corona disease. In fact, that is very much important. So the coconut oil is one of the remedy. Nobody knows it. So the palmitic acid is which acts against your the virus. And you also have unsaturated fatty acid in vegetable oils, which is oleic acid, linoleic acid of different 9, 12, 15, and resolenic acid. In fact, one of my students did a project on resolenic acid based polyurethane. This OH group, it is made to react with the NCO. So you can get polyurethane from resolenic acid based polyurethane, which he has combined with the polylactic acid and made a wonderful film for packaging application. So there are plenty of chemistries possible as far as this saturated and unsaturated fatty acids are concerned. So you can have oil modified polyesters. So that is possible by reacting oils, polyhydric alcohols, and polyfunctional acids. So you can get the corresponding oil modified polyesters, and single largest quantity of solvent soluble polymers manufactured for use in surface coating industry. So coating industry is one of the largest consumer of this oil modified polyesters. So instead of using synthetic material, you can switch on to this bio-based oil modified polyester, which can find application as a protective coating. Then there are different types. You have very long oil polyester, which is greater than 75%. Then you have long oil polyester, which is 60 to 78%. You have medium oil polyester, 45 to 60%. And short oil polyester, which is less than 45%. And you can see each one of them finds application. So one with the 75% that is used for nitrocellulose coating, and the long oil polyester, it maintains coating as a brushing enamels. Enamel is opaque coating. And the other one, 45 to 60, you can see they are used for anti-corrosive primers. And the short oil polyester, it is used for original equipment manufacture coating. So you can see they have got different variation, different choices, and each one of them finds application in different field. And similarly, you can use dimer acid polyamides. Polyamides, basically, they are used for elevated temperature applications. So polyamides, you have amine plus acid. So that gives, it's again a condensation and polymerization. In fact, the synthetic polyamide, they are used for space environmentally stable applications like Kapton polyamides. They are used in NASA. So they find a lot of application for radiation resistance. So perhaps you can think of replacing the synthetic polymers with the biopolymers. So the dimer acid polyamides can be tried. So you can try to utilize or explore the functions of such biopolymers and try to use them accordingly. By a slight modification with chemical modification, it is possible. And polyamide epoxy. So epoxy is another fascinating material which finds application in encapsulant, which find application as a protective coating. It is also used as a matrix material for the fabrication of composites. They are all used for self-healing composite as well. and various applications of epoxy resin is witnessed. And you can try to make a combination of your epoxy resin with the polyamide, because polyamide has an active hydrogen group which is capable of interacting with your epoxy resin. So this is the oxidant ring which is responsible for the polymerization. So this is a monomer, diglycyl ethers of bisphenol A, which is made to interact with your polyamide. So what happens? This ring opening polymerization takes place. You get the corresponding network structure. It's a thermosetting polymer which finds plenty of applications as far as engineering field is concerned. So you can have a combination of polyamide epoxy. Then you can also use epoxidized oils. They are synthesized by reacting vegetable oils. Especially, soybean or linseed oils can be used with peracid or hydrogen peroxide. So that is called epoxidized oils, which again they are used as a plasticizer. So plasticizer is another material which reduces the viscosity of your stiff polymer. Plasticizer, in fact, the conventionally used plasticizer are diglycyl phthalate, dioctyl phthalate, which are very much toxic. They are highly carcinogenic. So the use of such materials should be avoided. In that case, you can try to use this bio-based materials, which can be used as a plasticizing agent as well. As you can see, plenty of lengthy chain carbon is there, which offers flexibility to your rigid system. So they can be tried along with the stiff material. So you can try to alter the stiffness and toughness of the material by using this epoxidized oils, which can be used as a plasticizing agent. You can also use polycaprolactone. It shows that polycaprolactone degrades in a bioactive environment such as soil. So where and all this polylactic acid is used, where the degradation time is more than 180 days, you can use this polycaprolactone. In fact, we have made a PLA PCl combination. That paper we have published in a very good paper, which is again used as a film material for packaging application. So polycaprolactone and related polyesters are water resistant. So they can be used for corrosion resistant coating as well, because water is the main culprit for corrosion. Therefore, you can try to use them as a mechanical barrier which prevents the entry of corrosive species to the metal parts. So this can be another interesting area students can think of. Then you have polyhydroxybutyrate and polyhydroxyvalerate. It is formed when bacteria is fed precise combination of glucose. So it is again it's a bacterial synthesis. So you can try to get this polymer from bacteria and then use them accordingly. So it can be used, for cases like water, carbon dioxide, and aerobic conditions. Since it undergoes degradation, it can be used as a biodegradable polymer for certain applications. Similarly, you can use cellulose, which contains 90% cellulose, while wood contains 50% cellulose, and they are employed in a variety of applications. So you can use carboxy ethyl cellulose, because the natural cellulose is not water soluble. Therefore, if you want to make it water soluble, you have to convert it into corresponding derivatives: carboxy methyl cellulose, ethyl cellulose, hydroxypropyl cellulose. In fact, they find plenty of applications in healthcare, especially for healthcare application, as a coating for capsule. They are used as a drug delivery material. So carboxy methyl cellulose or cellulosic derivatives, they are the one which are used predominantly in healthcare application. They are also, besides that, you can find the application of this material in coatings, detergents, food, toothpaste, adhesives, and cosmetic application as well. And this is some of the examples of your cellulosic material. And you can see the cellulose acetate, which is made in the form of film. Okay, that is why they call celluloid. As far as your film, this thing is concerned, it is called celluloid. And hydroxyethyl cellulose, its derivatives are used in thickener. There are cases where you have to improve the thixotropy, in which they are acting as a thickening agent. So in which you need to know the viscoelastic properties of this material. Maybe I would request the students to look into the applied science of your chemistry. The chemistry is general chemistry, that's very important. It's a basic. But using basic, you try to use them for applications. So that is where you have to bridge the gap. So you please think of how to use chemistry in applications. So thickening agent is a one which is used to increase the viscosity of any material. So this is called a thixotropic agent. which is based on cellulose. So methyl cellulose is used in foods, adhesives, and cosmetic, and it is a plastic employed in packaging as well. And you can also use pressure-sensitive tapes. Again, pressure-sensitive tapes are basically thermoplastic material. You can apply hand pressure for adhesive application. There are the tapes which you are seeing at how cellulose tape, which is based on your cellulosic material. So it can be applied by hand pressure. And chitin, again, it is obtained from animal. So its derivative chitosan possesses highly strength, biodegradability, and non-toxicity. The principal source of chitin, as I told you, it is obtained from crab shell. It's a macromolecule, and it is obtained by a partial deacylation of chitin, which can be done by mechanical way or chemical way. It is insoluble because as the crab shell is very rigid, and this can be used for various applications. So where and all you require the barrier property, probably you can try this. So chitosan forms a tough, water absorbent, oxygen permeable, biocompatible films, and is used in bandages and sutures. And it is also used in cosmetic and for drug delivery in cancer chemotherapy. And it carries a positive charge in aqueous solution and is used as a flocculating. Flocculating agent is used for water treatment, where the impure substances can be trapped by means of this flocculating agent. So one of them is based on your chitosan. And then you can also use polyamino acid, which is also obtained from bio source, or found in naturally occurring proteins. 20 amino acids from the building blocks of a variety of polymers. So polypeptides based on glutamic acid, aspartic acid, and valine are the most frequently used materials as far as polyamino acids are concerned. You can see their structures. So the structures can be modified. So these are all the structures which are very interesting to me as a researcher. When I look at this amine group, it is very fascinating. So when you react this material with the epichlorohydrin, probably you can try to have a epoxidized glutamic acid, which can be finding plenty of applications. So this amine can be modified into epoxidation. Then similarly, amine and acid, you can prepare amides. So you have to look into the functional group of this material and try to modify it according to your desire and make products or components and try to use them for specific end-use application. So that is what, as a chemist, you should be looking at it. Okay, so this is about polyamino acid. Again, they find as a drug delivery system. Similarly, particularly attractive for medical applications. So when you are looking for healthcare applications, this is the material which can be tried. Homopolymers of aspartic acid and glutamic acid, water soluble and biodegradable polymers. And similarly, you can use protein. Soybeans are grown primarily for their protein content and secondarily for their oil. So you can get it from soybean. A 60-pound bushel of soybean yields about 48 pounds of protein-rich meal and 11 pounds of oil. So US soybean production exceeded 2,500 million bushels in 2002 itself. Imagine how US people are tapping the protein. Similarly, you can see these are the structures: alanine, arginine, and glycine. Again, the functional groups are very important. You can see NH2COO, which is there, and C double bond NH is there. So you try to utilize these functional groups and make different products using the chemistry that you are familiar with. And these products can be put into use for various applications. Okay, so it's a soy protein, and you can see it is employed in paper coatings, and it can be also made in combination with casein for adhesive application. And it is also used for wood bonding application, and you can also make composites using this soy protein as a matrix material. So any reinforcement can be impregnated with this protein. Okay, so Sorona is a biopolyester marketed by DuPont company. Okay, so that is a company which makes a lot of polymer products. So they may make this product Sorona. Offers advantages over both nylon and PET by the virtue of softer feel, better dyeability. So you can find application in textiles as well by switching over to this material, because it will attract the dye. So you can have a better color finish, excellent water fastness, and UV resistance as well. So when you looking ahead of the biopolymers, so the challenges as far as the biopolymers are concerned, the competitions with an inexpensive commodity, because synthetic polymers are inexpensive as far as the biopolymers are concerned. But still, at the longer run, you have to consider this biopolymer as an investment. You should not consider this cost, because though the initial cost is more, but when you look at the durability and the sustainability, this is going to be much beneficial than the synthetic polymer. So you have to consider this as a investment. But when you look at the cost alone, it will be pretty expensive. So that is not your mindset. So you should have a different mindset as far as this biopolymers is concerned. And disposal of biodegradable polymers, or again, you cannot dispose it the place which is nearby. So you have to have an infrastructural facility for disposing this polymer. So you need to have a composting facility. You need to have a better degradable facility, so that you can make this polymer completely degradable. So that is again another challenge. So in the absence of suitable bioconversion facilities, biodegradable polymers are discarded in dyed landfills, which again pose a severe problem. Therefore, the purpose for which the biopolymers are brought into use, that becomes useless. So you have to make sure all these facilities are met, and you follow the guidelines properly, so that you really realize the importance of these materials. And besides that, as I told you, life cycle analysis is very important as far as the biopolymers is concerned. So there is a technique used to quantify the environmental impact of products during their entire life cycle, from raw material, extraction, manufacture, transport, use, and through waste processing. So the LCA is very much needed for this, not only for this biopolymer, even for other products as well. This LCA is pretty much inevitable. So that ends the topic of biopolymers. So since I spoke about biopolymers, you may be wondering, you were just boasting and preaching about biopolymers. So I just want to draw your attention in some of the works carried out in our lab as far as the bio-based polymers are concerned. So since I told you polylactic acid is one of the forerunner, and we have used polylactic acid for our study. In fact, the novelty of your work is the products that we make is exclusively meant for industrial application. So because people believe that biopolymers, they don't have enough thermal stability or barrier properties, that prevents many people not to go for biopolymers. In fact, we try to use or explore the other side of biopolymers, and we made industrial products, and that's why we were able to get patent for this. So we choose polylactic acid. In the polylactic acid, we have got different forms like amorphous polylactic acid, completely crystalline polylactic acid, and semi-crystalline polylactic acid. So among the three, we have chosen semi-crystalline polylactic acid for our study, and we have modified the polymer using the chemical pathway. So we have made a polymer blends, because polylactic acid is very brittle, and it cannot be made into film if it is used as such. That is why it should be blended with the different polymers. So we made a polymer blends, and accordingly we made a polylactic acid PCl, polycaprolactone, and PEG is polyethylene glycol, PU is polyurethane. So what we did is we made a combination of PLA with PCl, PLA with the polyethylene glycol, PLA with the PU. The reason why we have made this blend is polylactic acid is very rigid, and it also prevents its use for engineering application. Therefore, it has to be modified with the soft materials like PCl, PEG, and PU. When we do so, we were able to design materials for industry. So that is what we did. And since the biopolymers, they have inferior thermal and mechanical properties, we thought, why can't we use some inorganic materials to improve the mechanical properties of this polylactic acid? Accordingly, we have used zirconium oxide, and we also used TiO2. So the TiO2 and zirconium oxide were impregnated into PLA. We made a bio-based materials which are used as a coated abrasive product as well as packaging product. And the interesting part, when we added zirconium oxide, it improved the mechanical stability of your PLA. And interestingly, we found that the degradation also it is expedited. So as I told you, polylactic acid undergoes degradation in the presence of coconut. You can also expedite the degradation of PLA when it is mixed with the zirconium oxide. So that is also possible. That is conventional polylactic acid. It undergoes degradation in the soil at 180 days. Whereas the PLA, which is doped with the zirconium oxide, it undergoes degradation within 3 months' time. So in that case, you are expediting the degradation of your PLA by mixing it with the inorganic material as well. And for packaging application, biopolymers, they are prone to microbial attack. Therefore, we need to improve the antibacterial property, for which we made use of different organic fillers like peanut shell carbon. Peanut shell carbon is we obtained from peanut shell, so which is subjected to pyrolysis, wherein we were able to get peanut powder, carbon powder from peanut shell. So that was reinforced with PLA. We made a polymer organic composite, polymer inorganic composite, and polymer blends. So the majority of use, we were looking at the targeted application of the study is coated abrasive. Coated abrasive, I think you would have seen emery paper. Emery paper, they find a lot of application for civil engineering applications. Say, for example, if I want to do a coating of wall in my house, I have to first remove the initial layer. So I have to do the rubbing, which creates a profile on your wall. Only then, it's just like how do you apply a powder? You cannot apply a powder without washing your face and drying it properly. If you apply it as it is, then it is not going to give you a very good finish. So in a similar fashion, the walls need to be created a profile for which the abrasive materials are pretty much important. So what we did is the conventional abrasives, the emery paper, which is made using synthetic polymers like acrylics, varnish, and all. So what happens during when we have a craft paper over which we apply a synthetic resin. So you have a craft paper which is degradable, over which you apply a synthetic coating, and over which we apply a abrasive particle. So that combination becomes a coated abrasive material. So the coated abrasive, basically what it does is, the synthetic material, when it is applied on craft paper, it becomes the paper becomes non-degradable. So it makes the degradable nature of paper into non-degradable. So after the use, what happens? The synthetic polymer based coated abrasive, after usage, that becomes a very big threat for the environment. It becomes very useless material in adds to solid waste management. Therefore, in order to avoid this, what we thought, so why can't we replace the synthetic resin with bioresin? So accordingly, we have replaced the acrylic and varnish coating with the bio-based material. So we have replaced the PLA as a coating material for paper. And the beauty of this technique is we were able to reduce the coating thickness. So conventional coated abrasive, the coating thickness is 35 GSM, gram per square meter. Whereas in our case, the coating thickness is reduced to 9 GSM. So almost there is a substantial reduction in coating thickness, and without compromising the mechanical properties. So that is again another important thing we were able to achieve. So the coated abrasive applications, you can see paper, as I told you, which is conventionally biodegradable, that becomes a non-degradable material when it is applied a synthetic material. Whereas what we did is we have replaced the synthetic coating with the bio-based coating, thereby retaining the degradability of paper. Not only that, the product after use can be effectively disposed. That is possible. So the usage of biodegradable polymers as an alternative to precise the natural biodegradable paper component in coated abrasive product is a novel idea. So nobody has tried it before. We are the first one to have explored the possible use of polylactic acid as a coating material for paper, and we made wonderful products out of it. And we are the first one to have explored this. Therefore, our work functionally attempts to bridge the gap in research domain, which serves both as an academic interest as well as a possible solution to an industrial product's effective utility and disposal. So you can make a product which can be effectively utilized by the industry, and it can also be disposed in a proper way. And that's why the patent was given to us. Okay, so industrial application, as I told you, the non-degradable coating material, you have, as far as the varnish is concerned, it is 15 GSM. Whereas when you go for acrylic, the GSM is 35 GSM. So in our case, we were able to reduce the GSM to 8.7. So very thin coating with effective barrier property can be achieved. So PLA, and in our process, what happens, the conventional coating process, it requires a heating. Again, the heating process that involves cost. So in our process, we were able to reduce the cost because it can be done at room temperature. So the coating of paper using PLA, it is a room temperature process. Okay. Then the additional coating heating process, which is also meant for your conventional baking material. So this one, in this case, we are avoiding two heating. So in our case, only one heating is required. Unlike the conventional heating process, you have to have two different heatings. That can be avoided as far as our PLA is concerned. So the developed PLA product based abrasives, they are performing very well, superior to the conventional coating materials, and the weight reduction is achieved in our case. As far as the performance is also very good, which are the essential properties required for industry. So industries are basically looking at very lightweight material with very high performance. So that we were able to achieve in our product. So as you can see, we have made a comparison between different PLA. So we have used amorphous PLA and the semi-crystalline PLA. Since it is used for barrier application, the amorphous PLA does not provide the properties that we wanted. Therefore, that was not considered. So we have used the semi-crystalline PLA, and this polymorphism is exhibited by semi-crystalline PLA when it is subjected to differential scanning calorimetry. This is a technique where you try to understand the polymorphism of your material. There, for example, I think people would have watched the Onion movie. Onion is the same, the Ambi is the same person, but he becomes Remo and Onion. So the same person is just like isomer. Atoms having same molecular weight, different same molecular formula, different structural formula. So this one, what happens? PLA, the semi-crystalline PLA, when it is subjected to DSE, it shows this polymorphism behavior. So we were able to exploit this polymorphism behavior for our coated abrasive applications. This amorphous PLA does not show this polymorphism, whereas the semi-crystalline PLA showed polymorphism, which is beneficial for our coated abrasive product. So this we were able to achieve it by differential scanning calorimetry. So this was one of the findings in our research work. And we made a product accordingly. We made a coating and coated abrasive. As you can see, the coating thickness is very less, and we can see there is a tortuous path is obtained as far as your semi-crystalline PLA is obtained. As a result, besides PLA having methyl group, which is hydrophobic, this tortuous path, that is because of the semi-crystalline nature, which also adds the hydrophobic behavior of your coated abrasive product. Because as far as coated abrasive is concerned, the waterproofing is one of the main problems. Therefore, if you are able to improve the hydrophobic behavior of your product, I think you are the winner. So as far as our product is concerned, we have chosen hydrophobic material, which is PLA. Besides that, we were able to improve the hydrophobic behavior when it is exhibiting the polymorphism behavior. So this PLA, besides water resistant, because of the polymorphism, it was able to offer better set of properties which are ideally needed for the making of coated abrasive products. And we have also measured the coating thickness by means of SEM. This is the cross-sectional view. So this one is virgin paper. We did a SEM, and this is the profile of virgin paper, craft paper. After it is coated with PLA, you can see the pores are completely, it is filled. Okay, and we measured the coating thickness, the cross-sectional coating. So this one is virgin paper. As you can see, the coating thickness, it is 113.42 micrometer, But, after it is coated with the PLA, the coating thickness increased. So overall coating thickness is 148.16, but the coating thickness made by our PLA is only 9 GSM. So this is how a coated abrasive product is made. You have a craft paper on which you have a maker coat, which is normally a synthetic material, which prevents the degradability of your paper. So what we have done is, instead of synthetic material, we have made a biopolymer coating over craft material. Accordingly, we have made a coated abrasive product. Okay, so this coated abrasive product can be used for rubbing, cutting, grinding operation, which finds a lot of application in automobile industry. So you can see craft paper is taken, over its PLA barrier coating is applied in room temperature. So you have a first coat, then on top of which you have a second coat, then you have a abrasive particle, then you have a PLA based barrier abrasive coated material, which is used for this automobile application. Okay, and when we see the waterproof behavior, we found the varnish coated, they are not water resistant, so they absorb water. Acrylic coated, again they show water absorption. Whereas whenever PLA coated, you can see the water resistance is substantially or It is drastically reduced. That is because of the polymorphism and the hydrophobic behavior exhibited by your semi-crystalline PLA. So accordingly, we were able to publish this paper in a reputed journal whose impact factor is 5.126. So why I'm telling you this, not to project myself. In fact, the students, you can take simple work and then do it with the facilities, whatever facilities that you have in your college. You can have wonderful products, which is possible. So that is the reason why I'm just showing this slide. And this one impact factor is 5.126. And similarly, we have made a Pla Pcl blends in order to improve the properties. In this Pla Pcl blend, the coated abrasive thickness, even it is coming down to 3.5 GSM only. In the previous case, neat PLA, it gives 9 GSM. Whereas when we are choosing over to Pla Pcl, the coating thickness still reduces to a greater extent, 3.5, almost 3 times reduction in the coating thickness. But as far as the performance is concerned, they are pretty much improvised. The performance is very good, and PCL being an ductile metal, so what happens? PCL, when you are adding with PLA, it removes the stiffness of your PLA metal. That is what you wanted. You want a slightly flexible material than your PLA. Therefore, when you are adding PCL with PLA, you are able to improve the toughness, and not only that, besides toughness, we were also able to improve the performance of coated abrasive products. And again, we did a DSC. We found 10% of the PCL is enough to modify the properties of your PLA. Beyond 10%, what happens? There are 2 different melting points are coming. As you can see, this is a virgin PLA. When PLA is added with the 10% PCL, there is no change. Whereas 15%, you can see there is a small hump coming over here. This is because of the melting temperature of your PCL. Then 20%, you can see one more peak. It is predominantly zinc. 15%, you can see it clearly. Therefore, what happens? When you keep on increasing too much percentage of PCL, you get 2 different melting points, which is not the thing that we wanted. Therefore, we optimize the percentage of PCL in PLA 10%, and the melting point is not even disturbed. 10% of PCL, when it is added with PLA, the melting point is not compromised. You can process the polymer in the same melting point of your PLA polymer. And we have also studied the interaction, because as a chemist, we cannot simply say they have an interaction. So only by means of FTIR, since it is happening on the surface, we thought the FTIR interactions can be used as a proof for the interaction between PLA and PCL. As you can see, this is the neat PLA, and it has a carbonyl stretching, which is a characteristic peak of your polylactate, C-double-bond-O stretching and COC stretching. So what happens when you are mixing it with PCL? The intensity of the peak is also reduced. So the peak intensity reduction, also there is a shift of IR peak towards the left-hand side or right-hand side, whatever it is, that indicates a proper interaction between PLA and PCL. So this paper was also published in a reputed journal, and whose impact factor is 3.1. So this one was published in Journal of Polymer Research in the year 2020. So this was also done by my PhD student, Mr. Sundar. And similarly, we were also able to make PLA PEG combination. Instead of PCL, we were also mixed PEG with PLA, and accordingly we did the same thing like a DSC. Again, here 10% PEG is enough to modify the properties of PLA, and PEG again it toughens the PLA. It improves the flexibility of PLA and barrier properties of PLA, and we were able to understand the interaction between PLA PEG using IR, and accordingly it was reported. And this paper was also published in Journal of Applied Polymer Science, whose impact factor is 3.125. And again, as far as the blend is concerned, PLA is again made to interact with the polyurethane. Polyurethane is a soft material, PLA is a rigid material. So when we mix polyurethane with the PLA, we were able to observe some semi-interpenetrating polymer network. So interpenetrating polymer network is another fascinating area of research, where you have a physical entanglement. It is not a chemical linkage between your PLA and PU. It's a physical entanglement which offers some unique combination of properties. So we were able to observe semi-interpenetrating network between PLA and PU. So this paper won the best paper award in an international conference that took place in 2020. So again, we were able to study on each case, you can see the polymorphism of PLA is not getting affected when it is mixed with the PCL or PEG. So the polymorphism remains unaltered. So meaning is that this polymorphism is responsible for offering barrier property. So we are not compromising the barrier property or the polymorphism when PLA is mixed with the PCL. Okay, so that is another important thing, and we were able to understand the semi-interpenetrating network by IR. So again, there is a shift of vibration frequency which indicates the interpenetrating form. And this work, we are really very happy to share this work. This one, the inorganic pigment was supplied by VIT University, Vellore, and they have given this TiO2 doped Bi2Ce 1.5 Ti 0.507. So which is basically an inorganic compound. It's a green pigment. They call it as a green pigment. And we were able to vary the composition of the green pigment from 1% to 5%. When we incorporated this green pigment with PLA, we were able to make films which are IR reflective and UV resistance. So this was the findings that we were able to observe from our study. So inorganic pigments can be impregnated with the PLA. We made IR reflective films. And this paper was published in an open access journal that was in the year 2020. Okay, so again, we did the characterization by means of your IR, and then we also measured the absorbance. Okay, so you can see the heat, the temperature is substantially reduced. So this films can be applied as a film over your car windows, because during summer and all you will encounter a lot of heat. So when this particular film is applied as a sticker, or it can be applied as a coating, what happens, you will feel only less temperature inside your car. But for that you can use this, and you can see 71.8% of IR radiation is reflected back when you are using this particular film. And similarly, we were also able to make PLA inorganic film composites, and we were able to study the interaction. And zirconium oxide, as I told you, it was able to degrade the PLA to a greater extent. And this paper was published in a very good journal, Composite Communication, whose impact factor is 6.2. Okay, and similarly, this one we made a polymer composite. That is polymer material matrix PLA. Reinforcing agent is your peanut shell carbon, and Schiff's base as well. Schiff's base, as I told you, they have got excellent antibacterial property. Therefore, when you are reinforcing Schiff's base with PLA, the antifungal properties of your PLA can be improved. So that paper was also published in the journal, that is Journal of Applied Polymer Bulletin, whose impact factor is 2.87. And this paper we are now trying to apply a patent. That is why no paper is published in this work. So we have taken the peanut shell, which is subjected to pyrolysis. We get the carbon powder, and that carbon powder obtained from pyrolysis of peanut shell is reinforced with the PLA. And we were able to study the antifungal property. We found that neat PLA film during this work we did it in lockdown. So all the work was done by our students. So I'm only the talker. So the doers are my students. So this work was done during the lockdown period. Neat PLA did not have this antifungal property. Whereas when you reinforce natural carbon with the PLA, you can see the antifungal property is substantially improved. You can see this one is neat PLA film, which is completely vanished after 1 week time, testing time. Whereas you can see no fungal growth is observed on a PLA peanut shell carbon film. Okay, so when you look into the summary and conclusion, we have used the semi-crystalline PLA for our study for the making of coated adhesive and packaging film, and we were able to make 10% of PCl with the PLA, which is ideal for both coated abrasive and packaging. And PLA PEG of optimum blend composition exhibit better set of properties. Again, that is can be tried as a packaging material. PLA with the castor oil, it forms a semi-independent network, which is used for wood coating application. Especially for wood coating, you can try this. And PLA with the zirconium oxide has provided enhanced mechanical properties in comparison with the neat PLA. Then we were able to make IR reflective yellow inorganic pigment loaded PLA films. And PLA peanut shell carbon composite exhibits better mechanical, thermal, antifungal, and antibiotic properties that are really needed for industrial products. So overall conclusion, modified PLA coated paper has been used as a base for coated base. As I told you, when you are using synthetic polymer as a base coating, the paper becomes non-degradable. Therefore, that is the reason why we have used biopolymer based coating. And the modified PLA barrier coating possesses the following properties. That is, they improve the mechanical integrity of the paper. They have very good compatibility with the paper and integrate the resin bonding system. Not only with paper, it was able to attract the abrasive particle as well. As a result, the entire product is completely unique and it is degradable as well. So that clearly indicates that modified PLA has tremendous potential for coated abrasive and packaging product, and we were able to reduce the coating thickness to a greater extent. 9 GSM, 3 GSM coating thickness can be made without compromising the barrier property or mechanical property. And finally, you can say PLA-based biodegradable synthetic polymer coated paper products can serve as environmental friendly recyclable product at an affordable cost. And these are some of the products which we are now working, a group. We made a membranes, PLA PCL membrane for water treatment. Similarly, we were able to produce PLA with cashew nut shell liquid, cardinal. We get wonderful, membranes. Similarly, PLA with polyhydroxy butyrate. This is again used as a membrane. And PLA with the PEG. And we were also involved in the development of formaldehyde-free phenolic resin. So formaldehyde is a neurotoxin, especially it interacts with the central nerve system of children of age less than 10. That's why it is banned in the United States of America. So we thought, why can't we make a formaldehyde-free phenolic coating? So we have used phenolic resin from castor, cashew nut shell oil, and formaldehyde, which we were able to obtain from natural process like inhaling and exhaling. We were able to get formaldehyde. Because an incomplete combustion in our body, that gives you formaldehyde. So that was this one was again, we applied a patent. We are yet to get the result. So this one is applied as a anti-corrosive coating on mild steel. Since phenolic resin has a lot of aromatic ring and chemical resistance, we thought it can be used as a protective coating. So here in this case, it is not synthetic formaldehyde, phenol formaldehyde coating. It is a natural phenol formaldehyde coating. Similarly, we have also used zeolites, natural materials, as an encapsulant for retaining biocides. Biocides, we again used natural biocide like champaka leaves, which is predominantly available in Coimbatore, which has got a unique antifungal and anti-corrosive property. And neem has been used in India for more than 5,000 years, and it has got very good antibacterial and antifungal property. So the purpose of zeolite is to retain the biocides within the pores. And you can see the pores, the zeolite structure, surface of the zeolite is modified. That is due to chemical reaction only. So the zeolite has got a free OH group. When it is made to interact with your coupling agent, you can get different functionally terminated biocides. I'm sorry, functionally terminated zeolites, in the pores of which you can load the biocidal material. So that is what we did. So what we did initially, we loaded the biocides into the pores of zeolite, and the surface of the zeolite is modified using chemical pathway, and we were able to produce functionally modified or functionally terminated zeolite containing biocides. This NH2 is capable of reacting with epoxy resin, so we have used epoxy resin for coating. So once we react this functionally terminated zeolite containing biocide with epoxy resin, we were able to realize sustained release of your biocide into the atmosphere, because biocides, when it is released instantaneously, it is not going to provide any use. It will be available for only certain period of time. Whereas when it is retained in an encapsulate like this, you can try to alter the release rate of your biocidal material. So the purpose of zeolite, eliminate the undesired contamination due to controlled release and low toxicity to human and other non-targeted organisms. No mutagenic effect can be felt when you are retaining the biocide within the zeolite, and sufficient wettability can also act against UV and weathering and long-lasting applications. And this one is very fascinating. This fruit was available in Anna University campus. It is called Stercula foetida. what we did, it is serendipity invention, I would say. So when myself and my student were talking and walking in the campus of Anna University, we found this fruit really fascinating. So what we did, we plucked the fibers from the fruit, we processed it, and the processed fibers were reinforced with the PLA in epoxy, and we made a wonderful composite. And we won the best paper award in 2017 in an international conference that held in Anna University. So these are all the natural materials, which are available plenty. So it is up to us to utilize them and use them accordingly. So this one was very fascinating, and really this is able to improve the mechanical properties of the composites. So when you look at it, biocomposite area, you can look into short natural fiber research. This is for the students, I'm telling you. Utilization of waste to wealth material. Then long natural fiber can be used. Utilization of residual flax, hemp, grasses. Okay, you can even alter the aspect ratio. Aspect ratio is nothing but length by diameter ratio. So greater the aspect ratio, greater will be the performance of your product. Therefore, the aspect ratio can be altered when you are using a long natural fiber. Then biopolymer development research, utilization of different vegetable oils, because I have indicated about vegetable oils. There are plenty of vegetable oils available. You can see they are used in various engineering applications, from medicinal field, cosmetic, coating, composites and all. So you try to use them accordingly. And again, you can also use the fiber orientation, fiber structure, geometry. Accordingly, you can develop different products. And you see different fibers are available in the form of powders as well. You can take coconut shell that can be made into powder. In fact, we made a coconut peanut shell, and then we made a carbon out of it. Similarly, you can also use coconut shell and then do it. Similarly, walnut shell. These are all the waste material. You convert it into useful material. Try to convert it into powder and then reinforce with the polymer, make a composite. Similarly, rice husk. We have also made a wonderful product using rice husk. It is used for oil filtration. So that project we have submitted to DST International Program in Portugal. So we have made a good products using this natural materials. And you can also use solvent. Eco-friendly solvents can be tried in case of synthetic solvents. So these are all the bio-based solvents you can try in place of synthetic solvents. So overall conclusion, the natural polymers and fibers, they've got enormous potential, as you have witnessed from the slides which I've showed you. I think they've got plenty of potential to be used in components for automotive industry, medical industry, cosmetic industry, healthcare industry, civil engineering industry, geotechnical industry, and it will offer cost savings, environmental benefits, and reduced component weight, which is the need of the hour. So when you are reducing the weight, that is something you are contributing to the earth. And the issues of toughness and variable, as I told you, that can be altered. That is where your chemistry part comes into picture. How to alter the properties of your material: toughness, stiffness, chemical property, mechanical property, barrier property, antifungal property. All these places where chemists play an important role. So the role of chemist is really it is required, and phenomenally it is increasing day by day. They cannot live without chemists. That is what one should understand. We are omnipresent and omnipotent. So natural products are not confined to auto. As I told you, it cannot be confined only with the automobile industry. It can be explored to various sectors as well. So partners and publicity, you can collaborate with Anna University, are most welcome. I'm looking forward to your collaboration, because from your principal, I heard that the Department of Chemistry has got very good H-index, very good research potential as well. So I'll be really happy to work with you. And you can also think of producing lightweight composite material. This is what tried by your Henry Ford in 1901. Okay, so at last, I would like to thank my students. Without their research work, the contribution, I'm nothing. So I really owe a great thanks to my students. I'm grateful to them, and they are the doers. As I said, they are the doers. I'm the talkers, and Raju is also working in a company, a coating company, and Sundar, he only last week he finished a doctorate. So he's the one who brought me patent. So this guy works in ITC company, and Keethana, a very interesting and enthusiastic student who is working on preparing scaffolds, 3D printed scaffold for breast cancer. and Jovan Stanley is working on developing bio-based polymer capacitors in the form of foils. It can be used for various applications. And Akin is used. He is working in the development of electrochemical sensor for pesticides removal. And Vanisri is an MSc student who worked with me for the development of PPAL fiber reinforced polylactic acid composite. And Pavitra, she was my MTech student. Presently, she is with IIT Madras. She was also working with the Carbondum Universal. So Pavitra and Sundar were, they were working together for the development of PLA-based products. So I once again thank you for your patient listening, and I thank my university for allowing me to present, to share some of my research work with your students. Sorry if I have taken too much time. Sorry if I have bored you. I hope you enjoyed. I'm really looking forward to receive questions from the audience and the faculty members as well. I thank the Guru Nanak College for taking this initiative, the principal and your HOD of the department, and the madam, all the staff members, students, for your patient listening, and thanks a lot. So any questions, please, I'll be very happy to answer your questions.
Madam, AK Madam.
Sir, there is one question from student Sabari Ganesh.
Yeah, please.
He's from second MSc. He has asked, by using biopolymers, can we develop ligand-based drug design?
Can we use biopolymers for?
Ligand-based drug design.
Biopolymers, so far, it is used for drug carriers, ma'am. It is used as a carrier. Okay, drugs and all, it is a very big area because minimum 15 years are required. If you are developing a new drug, it should reach market only after 15 years. It should get FDA approval. So I would prefer students not to work on this area because it's a lengthy process. So what you can do, you try to use the existing drug, try to modify it by chemical pathway so that there won't be any issue. That's what we did. We have taken sesamol, sesamic acid. Sesamol is obtained from your nallanai. So that we have used it for cardiovascular disease.
Yes.
So that paper was published in Royal Society. That is New Journal of Chemistry, RSC Advances and all. So we have done lipoic acid, which is again obtained from spinach. So these are all the products which are already existing in the market, which is FDA approved. So maybe you can try that. Maybe this biopolymers are used as a carrier. Once it goes inside the body, after the usage, it becomes the excipient. So nothing wrong. Even if it goes inside the body, it is not going to cause any harm to your body.
There is another question, sir, from Radha Varshani. Actually, sir, usage of biopolymers in food packaging is often reported that it spoils the taste of the food. Is this because of thickeners and the biopolymers itself? What can be done to address this issue?
Use of biopolymers for food packaging, okay. And the other question is?
What can be done to address this issue? Actually, she's saying the food taste is altered because of the thickeners and the biopolymers itself. She's asking, is this because of that? She's asking. And what can be done to address this issue? She's asking.
Okay. So, in that case, you try to avoid too many ingredients into that. So, it's better. In our case, we have only added PLA and PCL. No other additive is added. And we are also looking for natural material like peanut shell carbon.
Excuse me, Dr. Ananda Kumar.
Yes,
could you please stop your presentation because it is disturbing the live presentation, it seems. Okay.
I will do that. I will do that, ma'am. 1 second.
Thank you. Thank you.
Is it stopped now? Still it is coming?
No, it stops, sir.
No, it's coming, sir. Not close.
Okay, then I will stop it here. I think it's gone now.
No, still it is. Okay. Good.
Yeah, now it's all right, sir.
So what my suggestion would be, try to use natural material. As I told you, natural materials in the form of powders, fibers. Many forms are available as far as natural materials are concerned. try to use them accordingly. So that is what my suggestion would be. So if you switch over to natural material, probably this problem may not occur.
Okay, there is another question from Dr. Madhivanan.
Yeah.
Sir, which polymerization method is efficient for the synthesis of biopolymers?
I guess so, because a lot of technology is available right now. As far as biotechnological pathway, many industries are producing polymers by biochemical pathway. And as far as PLA is concerned, there are only 2 companies, not in India, in Canada and US. It's called Cargill. They are the one who produce large tons and tons of polylactic acid. Probably,
No, sir, he's asking which polymerization method is efficient for the synthesis of biopolymers.
For which polymer you is asking?
Polymerization method.
I indicated different polymerization method for different polymers. Okay, so you have to use the right polymerization for the right polymer.
Okay, it is not specific, and then accordingly we have to choose.
Yeah. So say for example, you take polylactic acid. So as I told you, it is patented work, which is the product of Cargill company. So they have their own method. So they do this monomerization and then do the polymerization, and they produce tons and tons of polymers.
Okay.
So you have to use the method accordingly.
Sir, I have my own question. Actually,
Yes,
what area you will suggest for the chemist to become an entrepreneur in this area?
Yes, madam. That's what I wanted actually. There are lots of scopes for students to become entrepreneurs. Plenty of products can be made. That is why I want our general chemistry students to look into the applied side, so that it will be great.
No, sir, I'm asking in the biopolymer area, specifically which one you will suggest?
For me, since I have used polylactic acid, I would recommend polylactic acid.
Okay. Nowadays, in the commercial use, biopolymers are used.
It is established one, and then it needs a lot of modification. That is where your chemistry people can come in and then do the modification. That's what we did. We did the modification. We took the polymer from the commercially available polymer only we have taken, and all we did is a chemical modification.
Okay, and for researchers, which area you will suggest in the biopolymer area?
Biopolymer area, now I said the healthcare is just catching up. As you see from the mask, now masks are being made using biopolymers. So instead of conventional masks, because we are now trying to make masks which can absorb 40% of the oxygen from the atmosphere. That's what we are trying right now.
Of course, but this is seasonal. Only in the pandemic it will be useful, sir. Forever.
Yes. That's why we are now working on membranes. Membranes can be used for gas absorption. So we are trying to make masks which can absorb 40% of the oxygen from the atmosphere. So we are now trying on it. That project is still going on. So that is another area. Healthcare sector is one other fascinating area. And this coated abrasive, as I indicated, they've got lot of potential, madam. Coated abrasive, huge company is Carborundum Universal. Murugappa Group, they've got very good turnover. And they are looking for natural material because they are importing material from abroad. So now the students can develop a natural material. Probably, you can try to supply material from here, India itself. So it becomes our Modi's dream may come true. Because self-sustainable, that is possible.
So a small request from the participants. All of you kindly unmute your video so that we can take a screenshot, all of you.
I would like to receive questions from the students. I'm very sorry if I've taken too much time. I think.
No, sir. Students.
Madam.
Students, if you can ask your questions.
From the bottom of my heart, I ask your apology because I didn't notice the time. Since I started,
No. It's not a problem, sir. No issue.
Very sorry.
All of you kindly unmute your camera, please. Video unmute.
Madam, not able to turn on my camera.
Dr. Anand Kumar, could you please? Students, if you have any questions, you are welcome to ask.
Good afternoon, sir. This is Noor Jahan. assistant professor from Guru Nanak College, our Department of Chemistry, Nanak College.
Good afternoon.
First of all, thank you, sir. Thank you for sharing your vast research experience, especially with PLA, using PLA with us. It was really informative, sir.
Thank
I
you.
have a doubt, sir.
Yes, ma'am.
Sir, you said that you are using zirconium oxide.
Yeah.
Won't it add for that heavy metal contamination after degradation?
That's a good question, actually. This was a question raised by the reviewer of the journal, Composite Communication. So I could see the real potential, from your staff members. That's a very good question. Actually, interestingly, zirconium, what happens, it increases the soil richness. After it degrades PLA, the soil richness is increased. And we have reports as well. So that reference only we have quoted. So it increases the soil virginity after it is getting degraded. So that is really, very interesting thing. So this question was raised by the reviewer of the Composite Communication. So such a good question, ma'am. Thank you. So we made sure that it contributes for the soil richness, and that is why it was accepted. That is why it was accepted, by the way.
Okay, sir. Thank you, sir.
Thank you, ma'am.
Students, please unmute your mic and you can ask directly, students.
I would like more students to ask me questions, and my talk becomes complete if I receive a question from student. Otherwise, if I don't receive a question, it is completely not understandable, I guess.
Sir, some of the questions Madam read was by the students only.
Okay.
Yes,
You can let the students to talk. You can make them talk and interact with me.
Yeah, that would be nice.
They can come out of the fear. They can ask me. In fact, I'd be very happy to address the students.
No, sir, some have joined through YouTube link. There they have posted the questions.
Fine. So only my concern was it was too much. I'm very sorry. I didn't notice the time.
No, not at all, sir. It was a very interesting topic, and I am sure our students have benefited a lot from that.
Please, I'm looking forward to your feedback, madam. Any negative feedback?
Definitely, sir. Definitely.
Because I would like to improvise
to you, sir.
So instead of positive feedback saying excellent and all, I don't want that. So I want only.
No, we will definitely send you the feedback, sir. We will be posting it to the students.
So that now I used to take it seriously. I work on it and then make sure that is not repeated in the next presentation. That's how
definitely. We will pass it on.
Okay. And my sincere thanks to your principal. It was so good to hear such good words about chemist. I was really overwhelmed.
Thank you.
When he was appreciating your staff members, I can see the potential of your department.
Thank you.
Really, I'm very happy, ma'am. Any help from Anna University are most welcome. We'll be happy to support you. In fact, we'd like to work with you.
Thank you so much, sir. We will definitely come and visit you in person, sir.
Yes. So any project also you can send your students final project.
Okay. Thank you so much, sir. I was going to ask you about it. Thank you so much.
You are most welcome. We have good lab. Your students can come. They can learn and also make us learn.
Yeah. Thank you, sir.
Rajeshwari, madam.
Yes, ma'am. Somebody was about to ask me something. Yes.
So good afternoon, sir. This is Raghavarshini from second year BSc Biotechnology, Guru Nanak College.
Good. Yeah, please go
I
ahead.
just want to ask, there is an allegation that 3D printers have a toxic effect on human. That is, as you are saying, polylactic acid particles are proven to be toxic more than the ABS particles. So what is this about? Can you address me with this?
I think you're right, because polylactic acid, it is prevalent in your body. So that makes you inert. The inertia comes because of polylactic acid. Okay, that's why it requires modification. And 3D printing, for which purpose you are asking? Because 3D printing is used for various applications. So which product?
So my question is, as we are using this polylactic acid in 3D
Yes.
printing and in also in medical field, as you
Yes.
showed a video about a mask which was also developed. So
Okay.
won't that affect us like
No,
humans
that
when
is
we
not
were
polylactic
using that?
acid. They have used a plastic resin. They have not indicated what type of resin it is. It's a plastic resin and it's a biopolymer resin, which is in the form of powder. So the process is called selective laser sintering. Okay, so they make powders and then they make a product by means of 3D printing. So they have not indicated the polymer resin. So that was not polylactic acid. So polylactic acid cannot be tried for all purpose. So you have to, as I told you, choose the polymer for right end use application. So you must be technically sound. That's what I'm telling you. Try to understand the structure property relationship of your biopolymers. That's why I have given various lists of biopolymers and their application. So you can choose them accordingly, which polymer you wanted for which application. Choose them and which processing method, which synthetic pathway, that and all with the knowledge that you have gained from your subject, you have to do it. So that is where your skill comes into picture.
Okay, sir. Thank you, sir.
Most welcome.
Rajeshwari madam, can you say a few words about this webinar?
Okay.
Madam, please.
Good afternoon to one and all present here.
Not audible, madam.
Your mic is
unmute your mic.
Okay. Good afternoon to one and all present here. I, Rajeshwari, on behalf of Department of Chemistry, feeling much privileged to propose the vote of thanks to our speaker, Dr. Ananda Kumar, Associate Professor, Department of Chemistry from Anna University. First of all, we are very grateful to you, sir, for accepting our invitation and spending your valuable time with us. Sir, you have enlightened us with your knowledge on biopolymers, and you have presented nicely about the biopolymers from the basics, its classification, its material properties, and also what is the need to prefer biopolymers in current scenario. You emphasize the importance of biopolymers and its application in engineering, medical field, and particularly in packaging industry. Our students are very much motivated, sir, by seeing the video which you played to choose their career in biopolymer field. Your patterns on the polylactic composites and how it is incorporated with the waste materials and how it can be made productive. It's very interesting, sir, and it is very informative to our students and for us also. I hope that our students definitely prefer their research in polylactic field in future. Once again, sir, I thank you very much for your informative, interesting, interacting and motivating sessions, sir. Thank you.
Thank you so much, madam.
Thank you, madam. Sir, again, Rangasamy is here.
Yes, sir. Yes.
I have to thank on my own part also as a
so nice of you, sir. So nice to get appreciation from my own group members. Chemistry, really, I would like to hear from more chemistry people.
Yes,
since we are in engineering, we hardly find they think that's why I say chemistry without science there is no engineering, and without engineering there is no technology. So I'm happy that I am receiving such good words from people from my own family. Yes, sir. Please go.
Thank you, sir. Actually, I just want to highlight a few things about this webinar.
Please go ahead, sir.
Actually, these days people are talking about green chemistry. One of the important principles of green chemistry is controlling the release of undesired byproducts, especially controlling the emission of CO2. Actually, controlling the emission of CO2 is an emergency need of the global requirement. Now, you have done a lot of work on this issue and you have contributed well towards the environmental safety in terms of controlling the CO2 and all those aspects. It also touching the concept of atom economy, again, another principle of green chemistry. Thank you very much, sir, for your dedicated research and effort on the environmental safety as well as on the biopolymers. And you have delivered a very systematic speech with specified objectives along with the evolution of polymers and the transformation of synthetic polymer to biopolymers. It's very quite interesting and it's very nice actually. This is the completely packed lecture or talk about the biopolymers. Okay, at this juncture, I want to once again thank you for your effort for the preparation and delivering the systematic talk. And I would like to thank our management and principal for giving the opportunity and giving the support to conduct these kind of webinars. And this is the time to thank all the participants, especially in this webinar. There are equal number of students as well as faculty members. Faculty members, even they have appeared from various parts of Tamil Nadu, from various government as well as private colleges. So that's very great and it's very appreciable. And I thank on my own department colleagues for their support for organizing this kind of webinars. And again, finally, I thank the Mr. Arun, GMC Media Center for live streaming the program in the YouTube channel. Once again, I thank one and all participating in the webinar. Thank you very much, sir.
So I'm touched, sir. I'm moved. I'm touched.
No, it's
honored. I'm honored. Such a huge gathering and addressed a very, what do you call, intellectual people.
Yeah. Thank you.
So nice.
Thank you so much, sir.
Shall we close, madam?
Yeah.